Good evening. Tonight what we're going to do is to work in sections 1-3 in our physics textbook, and what we're going to be looking at are measurements and graphing. Now let's move on to our graphing. We understand that independent and dependent variables are going to arise as we design experiments. And what we're going to be able to do is to put numerical data to interpret graphs, and we're going to be able to recognize from the graph common relationships that these two variables have with one another. The independent variable in physics very often is time, and that would be graphed on the x-axis. The dependent variable could be any one of a number of things, perhaps the distance traveled in that particular time, and that would be graphed on the y-axis. Whenever we name a graph, we always name the graph as whatever is plotted on the y-axis versus whatever is plotted on the x-axis. So here in our spring graph, we have the mass as our x-axis, and we have the length as our y-axis. So we want to name this graph the length of the spring versus the mass. Okay, so we see a difference as we go through, and it's certainly linear. Plots of data are going to take many different shapes, and we're going to be interested in three. The linear one that we just looked at, quadratic, that is a parabola, a parabolic shape, and an inverse curve, which is a hyperbola. We're going to discuss each one. So here is the linear relationship, and what we're going to be seeing is that we can eyeball, and it looks like it is going to be a straight line. So that's when we say, oh, I think it's a linear fit. So then we're going to learn how to find the best fit line on our calculator, and then we're also going to determine how we're going to be able to figure out if indeed this relationship is linear. This is an obviously linear relationship here, so it's pretty easy to tell that that's going to be the choice for the regression equation. This relationship between the two variables is called a linear relationship when y varies directly with x or indirectly with x, but basically it is going to have the shape of a constant slope, which makes it a line. We write the relationship in the slope-intercept form for a linear equation in physics because it's easiest to work with the slope, which is going to have real meaning for us, and the y-intercept so we can see how it shifts on the y-axis. So y is our dependent variable, m is the slope, x is the independent variable, and b is the y-intercept, or where the line crosses the y-axis. Keep in mind that to find the slope, we want to use the rise over the run, where we have the rise as the vertical change and the run as the horizontal change. So sometimes our slopes will be positive, high side on the right, and sometimes our slopes will be negative, high side on the left. It all depends on whether what is on the y-axis is increasing or decreasing with the increasing x-axis. So keep in mind that you're always going to be expressing the slope of a line as the rise divided by the run, or the change in y over the change in x. When x gets larger and y gets smaller, then we've got a negative slope, and the line will slope downward. When we are looking at the y-intercept, we want to make sure that we understand that is the y component of the ordered pair when x is 0. For nonlinear relationships, there are many of them. We're going to be looking at two specific ones. We're going to be looking at quadratic and inverse relationships. This is a quadratic relationship, It's a parabola, and in physics we only use the first quadrant because our time, for example, which is often on the x-axis, is never negative. There are lots and lots of things that if they were in the second quadrant, we would have a negative that cannot exist. So generally in physics our graphs are going to be first quadrant graphs. But that's a parabolic shape. The shape is a parabola and the type of graph is quadratic. A quadratic relationship is of the form that y is equal to kx squared, where k is a constant. We can also use other letters for the actual relationship. We talk about the quadratic equation in basic form, okay, in standard form, is y equals ax squared plus bx plus c. And in this relationship, the function y is going to vary with the square of x. Notice it's a lot more complicated than the linear equation. Here is a different graph. It's called a hyperbola, and a hyperbola is asymptotic. That means that it does not touch the axes, either the y or the x. And what we're looking at here is what graph appears when our y-axis, dependent variable, varies with the inverse of the x-axis. So this is an example of an inverse relationship. So on my pen on, sorry. An inverse relationship is shown by a hyperbola, and it is resulting when one variable is going to depend on the inverse of the other. An inverse relationship is basically of the form that y is equal to the inverse of x times some constant. So if I take a look at this, a lot of times they'll use k instead of a. So you might have something that looks like this. Y is equal to k over x. Now I like to state a inverse relationship differently. I like to actually multiply the x and the y here. Okay? So I like to remember it as x times y is equal to k, because for that we are going to be able then to find how x is going to vary with y, or in other cases how y is going to vary with x. And we can do that very easily by just making one little example. Here's an xy chart. That's another reason why I like to do it that way. But let's say that k, I'm going to just state that k, which is a constant, means it has to have a constant value. Let's say k is 12, okay? Then when x is 2, y has to be 6. When x is 3, y has to be 4, and so on. So you can very easily get statistical data points that you're able to deal with in order to determine and show an inverse relationship, a hyperbolic curve. The deal about graphs that makes them so useful is that we can derive relationships from these graphs to predict values that we don't know and we haven't not yet measured. What type of relationship is shown by the following graph? I hope you recognize it as, first of all, being a hyperbola because it's not touching either of the axes. That's a hyperbola, and a hyperbola is the shape of, think about it, an inverse relationship. Okay, so the relationship is inverse, the curve is a hyperbola. That should be pretty much squared away with you. Here's another one, the line of best fit. Now the line of best fit is always going to be the one that is drawn as close to all the data points as possible. It certainly is not going to join the first and last data points. Okay? It is certainly not going to join two centermost data points, and it's certainly not going to join the maximum data points on a graph. What we are looking at there is the line that fits closest for every one of those data points, so that we can determine whether or not the relationship is actually a linear relationship or not. Now let's take a look at this question, which you should be able to understand, that y equals mx plus b is the mark of and the equation for a linear relationship. That is going to be extremely important for us, and we want you to use the slope-intercept form y equals mx plus b whenever we are working with the linear equation.
Why, that's easy.